Welcome to Sleepy Science Odyssey. Tonight, meditation. The neuroscience of contemplative practices that have been refined over thousands of years. From the measurable changes in brain structure and function to the physiological effects on stress response systems. From attention training and emotional regulation to pain modulation and immune function enhancement. From ancient mindfulness traditions to modern clinical applications, from the default mode network's role in self-referential thinking to the neuroplasticity enabling lasting transformations. From breath-focused practices to loving-kindness meditation, from the molecular mechanisms of relaxation to the potential for meditation to slow cellular aging. We'll explore what happens in the brain and body during meditation, why these practices affect mental and physical health, and what science reveals about consciousness and the nature of awareness itself. If you're new here, this channel is for people who need something to think about before they can stop thinking. Real neuroscience and physiology, no exaggeration, just quiet facts in the dark. Let's begin. Meditation encompasses diverse practices involving focused attention, open monitoring, or cultivation of specific mental states, with effects measurable through neuroimaging, physiological monitoring, and behavioral testing. Meditation is not a single practice, but rather a family of techniques developed across various contemplative traditions, primarily but not exclusively from Buddhist, Hindu, and Taoist origins. Modern scientific investigation has identified several major categories of meditation based on cognitive mechanisms. Focused attention meditation, where practitioners sustain attention on a chosen object such as breath. Open monitoring meditation, where practitioners maintain non-reactive awareness of ongoing experience. And loving kindness or compassion meditation, where practitioners cultivate specific emotional states toward themselves and others. The scientific study of meditation began in earnest in the 1970s when Herbert Benson at Harvard Medical School studied practitioners of transcendental meditation and identified what he termed the relaxation response. A physiological state characterized by decreased oxygen consumption, reduced heart rate, and increased alpha and theta brain wave activity. This research demonstrated that meditation produces measurable biological changes, not merely subjective experiences, opening meditation to rigorous scientific investigation. Early meditation research faced methodological challenges, including small sample sizes, lack of control groups, reliance on self-report measures, and difficulty controlling for expectation effects. Practitioners often had thousands of hours of experience, making it unclear whether findings reflected meditation effects or pre-existing differences in individuals drawn to extensive practice. Modern research addresses these limitations through randomized controlled trials, active control conditions, neuroimaging techniques, and studying both novices and experts. Neuroimaging has revolutionized meditation research by allowing direct observation of brain activity and structure. Functional MRI, or fMRI, measures blood oxygen level-dependent signals reflecting neural activity, revealing which brain regions activate during meditation. Electroencephalography, or EEG, measures electrical activity with millisecond temporal resolution, identifying oscillatory patterns associated with different meditation states. Positron emission tomography, or PET scanning, measures metabolic activity and neurotransmitter receptor binding. Structural MRI reveals anatomical differences in brain regions associated with long-term practice. The default mode network, or DMN, discovered in the early 2000s, consists of interconnected brain regions including the medial prefrontal cortex, posterior cingulate cortex, and angular gyrus that activate during rest and self-referential thinking. The DMN is active when the mind wanders, engages in autobiographical memory, plans the future, or considers others' perspectives, activities involving the self. DMN hyperactivity has been linked to depression, anxiety, and rumination, making it a target for therapeutic interventions. Meditation appears to modulate DMN activity in specific ways depending on practice type. During focused attention meditation, experienced practitioners show decreased DMN activity compared to rest, suggesting reduced mind wandering and self-referential processing. This decrease is greater in long-term practitioners than novices, indicating that training strengthens the ability to disengage from default mental habits. Between meditation sessions, experienced practitioners show altered DMN connectivity patterns, suggesting lasting changes in how self-referential processing occurs. The posterior cingulate cortex, or PCC, a key DMN hub, shows particularly consistent changes with meditation practice. During meditation, PCC activity decreases in practitioners, and the magnitude of decrease correlates with meditation experience. Those with more practice hours show greater PCC deactivation. The PCC is implicated in self-referential processing and getting caught in experience rather than observing it non-judgmentally. Reduced PCC activity during meditation may reflect the cultivation of present-moment awareness without self-preoccupation. Studies comparing brain activity during meditation across different traditions find both commonalities and differences. Most meditation practices reduce DMN activity, suggesting this is a core feature of meditative states. However, focused attention practices additionally activate dorsolateral prefrontal cortex and parietal regions involved in executive control and attention, while open monitoring practices show less top-down control and more distributed patterns. Compassion meditation activates regions including the insula and anterior cingulate cortex associated with emotional processing and empathy. Long-term meditation practice is associated with structural brain changes detectable through MRI. Studies comparing experienced meditators to matched controls find increased gray matter density or cortical thickness in multiple regions including the prefrontal cortex, insula, hippocampus, and sensory regions. These differences correlate with practice hours. More meditation experience associates with greater structural changes. However, causality is unclear from cross-sectional studies. Meditation might cause structural changes, or individuals with particular brain structures might be drawn to sustained practice. Longitudinal studies, where novices are randomized to meditation training or control conditions, provide stronger causal evidence. 8-week mindfulness-based stress reduction, or MBSR courses, produce measurable increases in gray matter concentration in the hippocampus, posterior cingulate cortex, temporoparietal junction, and cerebellum. The amygdala, involved in stress and fear responses, shows decreased gray matter density following MBSR. These changes occur over weeks to months, demonstrating meditation can induce structural neuroplasticity in adults. The mechanisms underlying meditation-related structural brain changes remain under investigation. Neuroplasticity can involve multiple processes including neurogenesis, the birth of new neurons, synaptogenesis, formation of new synapses, dendritic branching, myelination, and angiogenesis, formation of new blood vessels. Animal studies show that environmental enrichment and learning induce all these processes. In humans, learning complex skills like juggling or taxi navigation produces structural brain changes in relevant regions, suggesting similar mechanisms might underlie meditation-related changes. The hippocampus, consistently showing structural increases with meditation practice, is particularly interesting given its roles in memory, spatial navigation, and regulation of the stress response. The hippocampus is one of few brain regions exhibiting adult neurogenesis in humans. Stress and depression are associated with reduced hippocampal volume, while antidepressant treatments and exercise increase it. Meditation may enhance hippocampal neurogenesis through reduced stress hormone exposure, increased neurotrophic factors, or direct effects of attentional training on hippocampal processing. The anterior cingulate cortex, or ACC, involved in attention, emotion regulation, and conflict monitoring, shows both functional and structural changes with meditation. The ACC activates when detecting errors, experiencing pain, or regulating emotional responses, functions requiring monitoring and control. Meditation practice increases ACC gray matter and alters its functional connectivity. Enhanced ACC function may contribute to improved attention regulation and emotional control observed in experienced meditators. The insula processes interoceptive awareness, conscious perception of bodily states including heartbeat, breathing, and visceral sensations. Meditation practices emphasizing body awareness, including mindfulness of breathing and body scan techniques, consistently activate the insula. Long-term meditators show increased insula gray matter, and this increase correlates with interoceptive accuracy, the ability to accurately perceive internal bodily signals. Enhanced interoceptive awareness may contribute to emotion regulation, as emotions involve bodily states and their cognitive interpretation. Brain oscillations or rhythmic patterns of neural activity show specific changes during meditation. Alpha waves at 8 to 12 Hz, associated with relaxed wakefulness, typically increase during meditation, particularly over frontal and central regions. Theta waves at 4 to 8 Hz, associated with drowsiness and light sleep, also increase during meditation, though experienced practitioners maintain alertness despite theta activity. Gamma oscillations at 30 to 100 Hz or higher, associated with attention and consciousness, show dramatic increases in highly experienced practitioners during certain meditation types. A landmark study of Tibetan Buddhist monks with 10,000 to 50,000 hours of meditation experience found extraordinarily high gamma wave activity during compassion meditation, far exceeding levels typically observed in laboratory settings. This gamma activity was sustained, high amplitude, and showed long-distance synchronization across brain regions. Novices trained in the same meditation showed smaller gamma increases, suggesting the effect scales with practice. The significance of these gamma oscillations remains debated, but they may reflect highly integrated brain states or enhanced conscious processing. The neural mechanisms underlying meditation's effects on attention have been extensively studied. Attention involves multiple components including alerting, achieving and maintaining vigilance, orienting, selecting information from sensory input, and executive control, resolving conflict among competing responses. Different meditation practices may preferentially enhance different attention components. Focused attention meditation emphasizes sustained attention and conflict monitoring. Open monitoring meditation emphasizes receptive awareness of all stimuli without selection. Studies using the attention network test, which separately measures alerting, orienting, and executive attention, find that different meditation practices affect different networks. Focused attention meditation primarily enhances executive attention, the ability to resolve conflict and maintain goals despite distraction. Open monitoring meditation enhances alerting and reduces attentional blink, the temporary impairment in detecting a second target following a first target. These differential effects suggest meditation practices can be tailored to enhance specific attention capacities. Sustained attention or vigilance typically declines over time in most tasks, a phenomenon called the vigilance decrement. Meditation training reduces this decrement, allowing practitioners to maintain attention over longer periods. In studies where participants detect rare target stimuli over 30 to 45 minutes, meditators show less performance decline than controls. This enhanced sustained attention may involve both bottom-up changes in arousal regulation and top-down improvements in maintaining task goals. Mind wandering, the tendency for attention to drift from intended tasks to unrelated thoughts, occupies approximately 30 to 50% of waking life in most people. Mind wandering is associated with decreased happiness and is a feature of many psychiatric conditions. Meditation training, particularly mindfulness meditation, reduces mind wandering in daily life as measured by experience sampling, randomly prompting participants throughout the day to report their thoughts. Reduced mind wandering correlates with increased well-being. The mechanisms by which meditation reduces mind wandering likely involve both decreased DMN activity and enhanced meta-awareness, the ability to notice when attention has wandered. Experienced meditators show faster reaction times in detecting mind wandering in laboratory tasks, suggesting they notice attentional lapses more quickly. This meta-awareness allows rapid redirection of attention back to intended objects, whether meditation objects during practice or task-relevant information during daily activities. Emotion regulation, the ability to influence which emotions one has, when one has them, and how one experiences and expresses them, is enhanced by meditation training. Multiple studies find that meditation training increases emotion regulation capacity as measured by self-report questionnaires, reduces emotional reactivity as measured by physiological responses to emotional stimuli, and enhances the ability to employ specific regulation strategies, including cognitive reappraisal, reinterpreting situations to change emotional responses. The neural mechanisms of meditation-enhanced emotion regulation involve multiple brain systems. The prefrontal cortex, particularly ventromedial and dorsolateral regions, implements emotion regulation strategies by modulating activity in emotion-generating regions, including the amygdala. Meditation training strengthens prefrontal amygdala connectivity, suggesting improved top-down regulation. Additionally, meditation may enhance bottom-up regulation through reduced reactivity in the amygdala itself. Experienced meditators show smaller amygdala responses to emotional stimuli even when not actively meditating. The amygdala, an almond-shaped structure in the temporal lobe, plays crucial roles in detecting emotional significance, particularly threats, and generating fear and stress responses. Hyperactive amygdala responses characterize anxiety disorders, PTSD, and depression. meditation training is associated with reduced amygdala reactivity to emotional stimuli. In one study, participants viewing disturbing images showed decreased amygdala activation after 8 weeks of mindfulness training compared to controls, despite no differences in subjective ratings of image unpleasantness. Compassion and loving kindness meditation practices explicitly cultivate positive emotional states and prosocial motivation. These practices typically involve generating feelings of warmth and care initially toward oneself, then progressively toward loved ones, neutral individuals, difficult individuals, and eventually all beings. Neuroimaging studies during compassion meditation show activation of brain regions involved in empathy, emotion regulation, and positive affect, including the insula, anterior cingulate, ventral striatum, and orbitofrontal cortex. Empathy involves both affective empathy, sharing others' emotional states, and cognitive empathy, understanding others' perspectives. Compassion extends beyond empathy to include motivation to alleviate suffering. Studies suggest meditation training enhances both empathy and compassion. Participants trained in loving-kindness meditation show increased activation in empathy-related brain regions when viewing images of suffering compared to controls. They also show increased helping behavior in laboratory tasks, measuring prosocial action. The distinction between empathy and compassion is important for understanding meditation effects on social cognition. While empathy involves resonating with others' suffering, which can lead to empathic distress and burnout, particularly in caregiving professions, compassion involves warmth and concern coupled with motivation to help while maintaining emotional balance. Compassion meditation training may buffer against empathic distress by cultivating caring responses without being overwhelmed by others' pain. Pain perception involves both sensory discriminative components, location, intensity, quality, and effective motivational components, unpleasantness, suffering, desire for pain to end. These components are mediated by partially separate brain systems. Meditation training modulates both components, but particularly affects the effective motivational dimension. Meditators report reduced pain unpleasantness even when sensory intensity ratings remain unchanged, suggesting they perceive pain sensations but suffer less from them. Neuroimaging during painful stimulation reveals that meditation alters pain-related brain activation patterns. Experienced meditators show reduced activity in pain-related regions, including the prefrontal cortex, amygdala, and hippocampus when experiencing pain during meditation compared to rest. They show increased activation in regions, including the insula and anterior cingulate, involved in interoceptive awareness and attention. This pattern suggests meditation changes the relationship to pain from emotional reactivity to non-judgmental observation. Mechanisms underlying meditation's analgesic effects appear distinct from placebo analgesia and opioid-mediated analgesia. Studies using the opioid antagonist naloxone find that naloxone blocks placebo analgesia, but not meditation-induced pain reduction, indicating meditation does not rely primarily on endogenous opioid release. Instead, meditation may work through attention mechanisms. Fully attending to pain sensations paradoxically reduces suffering and cognitive reappraisal, interpreting pain as sensation rather than threat. Clinical applications of meditation for chronic pain management show promising results. Mindfulness-based stress reduction, developed by John Kabat-Zinn at the University of Massachusetts Medical School in 1979, was originally designed for chronic pain patients. MBSR participants show reduced pain intensity and pain-related disability compared to controls in multiple studies. Effects are maintained at long-term follow-up, suggesting meditation provides lasting pain management skills rather than temporary relief. The stress response, mediated by the hypothalamic pituitary adrenal or HPA axis and the sympathetic nervous system, is essential for dealing with acute threats but becomes pathological when chronically activated. Chronic stress contributes to numerous health problems, including cardiovascular disease, immune dysfunction, metabolic disorders, and mental illness. Meditation training has been extensively studied for stress reduction, with multiple randomized controlled trials demonstrating effectiveness. The physiological stress response involves the hypothalamus releasing corticotropin-releasing hormone, or CRH, which stimulates the pituitary to release adrenocorticotropic hormone, or ACTH, which stimulates the adrenal cortex to release cortisol. Simultaneously, sympathetic nervous system activation triggers adrenal medullary release of epinephrine and norepinephrine. This cascade increases heart rate, blood pressure, glucose availability, and immune activation while suppressing non-essential functions like digestion and reproduction. Meditation training affects multiple components of the stress response system. Studies measuring cortisol find that meditation training reduces baseline cortisol levels and modulates cortisol reactivity to stressors. The cortisol awakening response, the sharp rise in cortisol in the first 30 to 45 minutes after waking, is dysregulated in chronic stress and depression. Meditation training normalizes this response. Cortisol has a circadian rhythm with highest levels in morning and decline through the day. Meditation training enhances the normal diurnal slope. The sympathetic nervous system mediates rapid stress responses through norepinephrine and epinephrine release. Meditation practice reduces sympathetic activity as measured by heart rate, blood pressure, and skin conductance. Heart rate variability, or HRV, variation in time intervals between heartbeats, provides a measure of autonomic balance between sympathetic and parasympathetic influences. Higher HRV indicates greater parasympathetic activity and better stress resilience. Meditation training increases HRV, suggesting enhanced parasympathetic tone and improved autonomic regulation. The parasympathetic nervous system, often called the rest and digest system, opposes sympathetic activation, promoting recovery and restoration. The vagus nerve mediates most parasympathetic influences on the heart and visceral organs. Vagal tone, estimated through HRV measures, reflects parasympathetic influence. Higher vagal tone is associated with better emotion regulation, social engagement, and health outcomes. Meditation training increases vagal tone, potentially contributing to improved stress resilience and emotional well-being. Breathing patterns influence autonomic balance through direct mechanical and neural mechanisms. Slow breathing at approximately 5 to 6 breaths per minute maximizes HRV and enhances parasympathetic activity. Many meditation practices involve natural slowing of respiration. Some practices, like pranayama, explicitly manipulate breathing. The physiological effects of breathing practices partly overlap with meditation effects, raising questions about how much meditation's benefits depend on breathing changes versus other mechanisms. Inflammation plays crucial roles in immunity and healing, but becomes pathological when chronic. Chronic inflammation, measured by biomarkers including C-reactive protein or CRP, and pro-inflammatory cytokines like interleukin-6 or IL-6 and tumor necrosis factor alpha or TNF-alpha, contributes to cardiovascular disease, diabetes, cancer, neurodegenerative disease, and depression. Stress promotes inflammation through multiple pathways. Meditation training reduces inflammatory biomarkers in multiple studies, suggesting anti-inflammatory effects. Mechanisms linking meditation to reduced inflammation may involve multiple pathways. Reduced stress hormone exposure decreases inflammatory signaling. Enhanced parasympathetic activity has anti-inflammatory effects through the cholinergic anti-inflammatory pathway. Vagal release of acetylcholine inhibits inflammatory cytokine production by immune cells. Changes in gene expression in immune cells alter inflammatory responses. Improved sleep, often enhanced by meditation, reduces inflammation as sleep deprivation is pro-inflammatory. Immune function encompasses innate immunity, providing immediate nonspecific defense, and adaptive immunity, providing targeted responses with immunological memory. Both branches show modulation by psychological states and stress. Meditation training affects multiple immune parameters, including increased antibody responses to vaccines, enhanced natural killer cell activity, and altered immune cell gene expression. The clinical significance of these changes remains under investigation, but suggests meditation may enhance immune function. Gene expression in immune cells changes following meditation training, as revealed by transcriptomic studies. One consistent finding is reduced expression of pro-inflammatory genes regulated by NF-kappa B, a transcription factor activated by stress and inflammation. This pro-inflammatory gene expression profile, termed the conserved transcriptional response to adversity or CTRA, is elevated in chronic stress, loneliness, and early adversity, and predicts negative health outcomes. Meditation training reduces CTRA expression, suggesting reversal of stress-related inflammatory gene expression patterns. Telomeres are protective DNA protein structures at chromosome ends that shorten with each cell division until reaching critical lengths triggering senescence or death. Telomere length correlates with biological aging and predicts longevity and disease risk. Chronic stress accelerates telomere shortening. Meditation training has been associated with slower telomere attrition and increased telomerase, the enzyme that maintains telomeres, in multiple studies, though effects are modest and not consistently replicated. One influential study found that a 3-month intensive meditation retreat increased telomerase activity in participants compared to waitlist controls. The increase correlated with improvements in psychological well-being and perceived control. Subsequent studies have found mixed results, with some showing increased telomere length or telomerase activity following meditation interventions, while others find no effects. Methodological differences including meditation type, duration, intensity, and telomere measurement techniques may contribute to inconsistent findings. If meditation does slow telomere attrition, potential mechanisms include reduced oxidative stress. Meditation decreases oxidative damage to DNA, which contributes to telomere shortening. Reduced inflammation. Inflammatory cytokines accelerate telomere shortening. Reduced cortisol exposure. Cortisol inhibits telomerase activity. And improved health behaviors including sleep, diet, and exercise that affect telomere maintenance. However, the biological significance of meditation-related telomere changes, if real, remains uncertain given the small effect sizes typically observed. Sleep quality and duration affect virtually every aspect of health and cognition. Sleep problems are epidemic in modern societies, with approximately 30% of adults experiencing insomnia symptoms. Insomnia involves both difficulty falling asleep and staying asleep, and is associated with rumination, hyperarousal, and anxiety about sleep itself. Meditation training improves sleep quality and reduces insomnia severity in multiple randomized controlled trials, with effects comparable to cognitive behavioral therapy for insomnia, the gold standard treatment. Mechanisms underlying meditation's sleep benefits likely include reduced rumination and worry that interfere with sleep onset, decreased physiological arousal through reduced sympathetic activity, enhanced parasympathetic activity promoting relaxation, and improved emotion regulation reducing emotional distress that disrupts sleep. Mindfulness practice may also reduce dysfunctional beliefs about sleep and catastrophizing about sleeplessness, which maintain insomnia. Some evidence suggests meditation increases slow-wave sleep, the deepest, most restorative sleep stage, though findings are mixed. Depression affects over 300 million people worldwide and is characterized by persistent low mood, anhedonia, inability to experience pleasure, cognitive symptoms including rumination and negative bias, and somatic symptoms including sleep disturbance, appetite changes, and fatigue. Depression often recurs, with each episode increasing risk of subsequent episodes. Meditation-based interventions, particularly mindfulness-based cognitive therapy, or MBCT, effectively prevent depression relapse with efficacy comparable to maintenance antidepressant medication. MBCT combines mindfulness meditation training with elements of cognitive therapy for depression. It teaches participants to recognize and disengage from depressive thought patterns and to adopt a decentered relationship to thoughts, viewing thoughts as mental events rather than facts. In individuals with 3 or more previous depressive episodes, MBCT reduces relapse rates by approximately 40 to 50% compared to usual care. Effects are particularly strong in individuals with childhood trauma, suggesting MBCT may help break trauma-depression links. The neural mechanisms underlying meditation's antidepressant effects likely include reduced DMN hyperactivity and rumination, enhanced prefrontal regulation of limbic emotional responses, increased hippocampal volume reversing stress-related atrophy, and normalized HPA axis function, reducing excessive cortisol. Additionally, meditation may increase monoamine neurotransmitter availability through effects on synthesis, release, or reuptake, though evidence for this mechanism is limited. Anxiety disorders including generalized anxiety disorder, social anxiety disorder, panic disorder, and PTSD affect hundreds of millions worldwide. Anxiety involves excessive fear and worry, hypervigilance to threat, and avoidance behaviors. Meditation training reduces anxiety symptoms across diverse anxiety disorders. Meta-analyses of randomized controlled trials find moderate effect sizes for meditation interventions on anxiety, comparable to cognitive behavioral therapy, and larger than medication effects in some studies. The mechanisms by which meditation reduces anxiety include extinction of fear conditioning. Repeated exposure to internal sensations without feared consequences extinguishes conditioned fear responses. enhanced emotion regulation, reducing emotional reactivity, decreased amygdala reactivity to potential threats, improved attention control, reducing attentional bias toward threat, and reduced worry and rumination. Importantly, meditation appears to prevent experiential avoidance, the tendency to suppress or avoid uncomfortable internal experiences, which maintains anxiety disorders. Attention deficit hyperactivity disorder, or ADHD, is characterized by inattention, impulsivity, and sometimes hyperactivity. ADHD affects approximately 5% of children and 2.5% of adults, and is associated with substantial functional impairment. Standard treatments include stimulant medications and behavioral interventions. Meditation training, particularly mindfulness training, shows promise for ADHD, though research is limited. Studies find that meditation training improves attention, reduces hyperactivity and impulsivity, and decreases ADHD symptoms in both children and adults. Substance use disorders involve compulsive drug seeking and use despite negative consequences, with high relapse rates even after treatment. Meditation-based interventions, including mindfulness-based relapse prevention, or MBRP, have been developed for addiction treatment. MBRP teaches individuals to recognize triggers and cravings without automatically acting on them, to tolerate uncomfortable emotions without seeking substance-induced relief, and to make conscious choices rather than automatic habitual responses. Studies find MBRP reduces relapse rates compared to standard treatment or support groups. The neural mechanisms underlying meditation's effects on addiction likely include enhanced prefrontal cortical control over impulsive responses mediated by striatal reward circuits, reduced stress reactivity decreasing stress-induced craving and relapse, enhanced interoceptive awareness allowing recognition of craving as bodily sensations rather than commands to use, and altered reward processing possibly reducing drug reward salience. Changes in brain connectivity between prefrontal regions and limbic regions observed following meditation training support these mechanisms. Eating disorders including anorexia nervosa, bulimia nervosa, and binge eating disorder involve disturbed eating behaviors, preoccupation with weight and shape, and emotion dysregulation. Meditation-based interventions show promise for eating disorders, particularly binge eating. Mindful eating practices teach attention to hunger and satiety cues, awareness of eating triggers, and non-judgmental acceptance of food-related thoughts and emotions. Studies find mindfulness interventions reduce binge eating frequency and improve associated psychological symptoms. Trauma-related disorders, including PTSD, involve intrusive memories, hyperarousal, avoidance, and negative alterations in cognition and mood following traumatic experiences. Meditation training for trauma requires careful consideration, as focusing attention inward can trigger traumatic memories. However, trauma-informed meditation approaches that emphasize safety, choice, and gradual exposure show promise. Studies find mindfulness-based interventions reduce PTSD symptoms including intrusion, avoidance, and hyperarousal when delivered by trained clinicians. Neurodevelopmental considerations are important for meditation applications across the lifespan. Brain development continues through adolescence and into the 20s, with prefrontal cortex maturation particularly prolonged. Children and adolescents may benefit from meditation training, but require developmentally appropriate practices. Studies of mindfulness training in schools find improvements in attention, emotion regulation, and stress resilience in children and adolescents, with larger effects in higher-risk populations. Aging is associated with cognitive decline and neurodegenerative disease in many individuals. Meditation training may help preserve cognitive function and slow brain aging. Studies comparing older long-term meditators to matched controls find better preserved gray matter, particularly in the prefrontal cortex and hippocampus, regions showing age-related decline. Older adults randomized to meditation training show improvements in attention, working memory, and cognitive flexibility compared to controls. Whether meditation prevents or delays dementia requires longer-term studies. Individual differences influence meditation practice and outcomes. Personality traits predict who initiates and maintains meditation practice. Higher openness and conscientiousness predict practice adherence. Genetic variation influences meditation effects. Polymorphisms in genes involved in neurotransmitter systems affect response to meditation training. Pre-existing psychiatric conditions influence both the appropriateness of specific meditation practices and treatment response. Recognizing individual differences allows tailoring practices to individuals. Adverse effects of meditation, while relatively rare, deserve attention. Meditation can trigger anxiety, dissociation, or psychotic symptoms in vulnerable individuals. Past trauma can be reactivated during practice. Meditation retreats involving extended practice can precipitate adverse experiences more frequently than less intensive practice. Systematic studies find approximately 25% of regular meditators report at least one adverse experience, though most are transient and mild. Screening for vulnerability factors and providing appropriate support and guidance can minimize risks. The mechanisms underlying adverse meditation effects are poorly understood, but may include over-effortful practice causing tension rather than relaxation, confrontation with difficult emotions or memories without adequate support, misinterpretation of normal meditation experiences like altered time perception or boundary dissolution as pathological, insufficient grounding practices, balancing meditative absorption, and pre-existing vulnerabilities including trauma history or psychosis risk. Properly trained teachers can recognize and address emerging problems. Meditation traditions distinguish between concentration states or samadhi involving absorption in meditation objects and insight practices cultivating wisdom and liberation. Modern neuroscience has primarily studied concentration and mindfulness practices, with less research on insight-oriented practices. Traditional descriptions suggest that deep practice can lead to shifts in self-understanding, perception, and relationship to experience beyond stress reduction and emotion regulation. Scientific investigation of these deeper transformations is in early stages. The neuroscience of meditation has largely focused on relatively short-term training, 8 to 12 weeks, in novice practitioners. Studies of long-term practitioners with thousands of hours of experience provide glimpses of expertise effects, but cannot establish causality. Longitudinal studies following practitioners over years as they accumulate practice would provide stronger evidence for progressive changes with sustained practice. Such studies are challenging, but necessary for understanding meditation's full potential. The role of belief and expectation in meditation effects deserves consideration. Participants in meditation studies typically believe meditation will benefit them. Expectancy effects could contribute to outcomes. Studies comparing meditation to active control conditions designed to match expectancies, show that meditation effects persist beyond placebo, though expectancies likely contribute. Dismantling studies comparing meditation components, for example, attention training versus ethical components, could clarify specific active ingredients. Cultural context influences meditation practice and interpretation. Meditation originated in religious and philosophical traditions with specific worldviews about the nature of mind, self, and reality. Modern secular applications like MBSR deliberately minimize traditional religious and philosophical content to increase accessibility. This raises questions about whether meditation divorced from original contexts retains full effectiveness or risks cultural appropriation. Research comparing secular and traditional approaches could address these questions. Contemplative neuroscience faces philosophical questions about the relationship between first-person subjective experience and third-person objective measurement. Meditation involves private subjective states that practitioners claim transform perception and understanding. Neuroscience can measure brain correlates of these states, but may not capture their full subjective richness. Phenomenological research interviewing practitioners about their experiences complements neuroscientific measurement, providing richer descriptions of what meditation is like from the inside. The hard problem of consciousness, how subjective experience arises from physical processes, remains unsolved. Meditation provides unique opportunities to investigate consciousness as practitioners systematically explore the nature of awareness through introspection. Some researchers propose that meditation could provide crucial data for consciousness science by generating highly trained first-person observers who can reliably report on subtle aspects of experience. Integrating contemplative first-person methodologies with neuroscience third-person methodologies represents a frontier for consciousness research. Neural correlates of consciousness, or NCCs, are the minimal neural mechanisms sufficient for a conscious experience. Identifying NCCs for specific meditation states could advance consciousness science. For example, if particular meditation states reliably correlate with specific patterns of gamma oscillations or network connectivity, this suggests those patterns contribute to generating those conscious states. However, correlation doesn't prove causation, demonstrating that neural patterns cause rather than merely accompany conscious states requires additional evidence. The Integrated Information Theory, or IIT of consciousness, proposes that consciousness corresponds to integrated information. A system is conscious to the degree it integrates information across its parts while remaining differentiated. Meditation might be investigated through IIT's lens. Does meditation increase or decrease integrated information? Do different meditation states correspond to different information integration levels? Such questions connect ancient contemplative practices to cutting-edge consciousness theories. Global workspace theory proposes that consciousness arises when information becomes globally available to multiple cognitive systems through broadcasting in a neuronal global workspace. Meditation might alter global workspace dynamics. Focused attention might narrow the workspace to meditation objects, while open monitoring might expand workspace access. Testing these predictions requires measuring information availability across brain systems during different meditation states using techniques like effective connectivity analysis. Predictive processing frameworks propose the brain continuously predicts incoming sensory data based on internal models, with prediction errors updating models. Meditation might reduce reliance on predictions, allowing more direct contact with sensory experience. Reduced DMN activity during meditation could reflect reduced generation of predictions about self and world. Enhanced interoceptive accuracy in meditators might reflect better calibrated predictions about bodily states. These hypotheses connect meditation to broader theories of brain function. Free will, the sense of being the conscious author of one's actions, is questioned by neuroscience findings that unconscious brain activity precedes and predicts conscious decisions. Meditation traditions often describe insight into the illusory nature of the self as agent, recognizing that thoughts and actions arise from conditions rather than from an independent chooser. Investigating whether meditation changes the phenomenology or neural correlates of agency and volition could illuminate the relationship between neuroscience and experiential accounts of selfhood. The self, our sense of being a continuous unified subject of experience, is central to human psychology, but increasingly recognized as a construction rather than an entity. Meditation traditions describe practices for deconstructing the sense of self, revealing it as a process rather than a thing. Neuroscience of meditation could investigate how self-related processing changes with practice. Do self-referential thought and neural signatures of self-processing diminish? Do meditators show reduced distinction between self and other in neural terms? Time perception is altered during meditation, with practitioners reporting that time passes differently. Meditation might slow subjective time by increasing present moment attention. Dense moment-to-moment experience makes duration feel longer, while mind-wandering makes time pass unnoticed. Alternatively, absorption in meditation objects might make time pass faster by reducing attention to time itself. Studies measuring time perception during and after meditation using duration estimation and temporal reproduction tasks could clarify these opposing predictions. Space perception might also change with meditation practice. The sense of where the body ends and environment begins, body boundaries, could become more fluid with meditation, reducing DMN activity involved in self-other distinction. Out-of-body experiences and boundary dissolution are reported by some practitioners. Investigating the neural basis of these phenomena during meditation might illuminate how the brain constructs spatial self-representation and the sense of being located in a body. Metacognition, cognition about cognition, is enhanced by meditation training. Meta-awareness of mind-wandering improves with practice. Meditators show better calibrated confidence judgments. Their subjective confidence better matches objective accuracy, suggesting enhanced metacognitive insight. The neural basis of metacognition involves frontopolar cortex and other prefrontal regions that show structural changes with meditation. Enhanced metacognition might contribute broadly to meditation benefits by improving self-knowledge and self-regulation. The neural basis of meditation expertise is beginning to be understood through studies comparing novices, intermediate practitioners, and experts with tens of thousands of practice hours. Expertise is associated with both increased efficiency. Experts show less effortful activation of control regions during meditation, and capacity. Experts achieve brain states novices cannot. This pattern resembles skill learning in other domains like music or sports, where expertise brings both automaticity and expanded capabilities. Intensive meditation retreats provide unique research opportunities by exposing participants to meditation doses far exceeding typical studies. Month-long or longer retreats produce brain changes and experiential shifts not observed in weekly meditation classes. Studies of retreat participants before, during, and after retreat track trajectories of change over time, revealing that some changes require sustained intensive practice. However, intensive retreats also present practical and ethical research challenges. The optimal dose of meditation for different outcomes is unknown. Casual practice, a few minutes weekly, likely produces minimal effects. Moderate practice, 20 to 45 minutes daily, produces measurable changes in weeks to months. Intensive practice, hours daily over months or years, produces larger changes. Dose-response relationships likely differ for different outcomes. Stress reduction might require less practice than structural brain changes. Identifying minimal effective doses would help tailor recommendations. Meditation delivery methods affect accessibility and adherence. Traditional approaches involve in-person instruction and group practice. Modern adaptations include apps, online courses, and virtual reality implementations. Research comparing delivery methods finds in-person instruction generally superior for learning quality, but app-based meditation increases accessibility and convenience. Hybrid approaches combining initial in-person instruction with app-supported maintenance practice might optimize effectiveness and adherence. Adherence to meditation practice is a major challenge. Most people who begin meditation practice discontinue within weeks or months. Factors predicting adherence include social support through group practice, accountability structures, gradual progression in practice difficulty, immediate positive experiences during practice, and integration with existing values and routines. Understanding adherence barriers and facilitators is crucial for translating research findings into real-world benefit. Mechanisms of behavior change in meditation interventions remain unclear. Is meditation itself the active ingredient, or do benefits arise from group support, expectation, instructor attention, or lifestyle changes accompanying practice? Component studies isolating these factors are rare but necessary. For example, comparing meditation instruction plus group support versus group support alone could clarify meditation's specific contribution. Neuroplasticity underlying meditation effects likely involves molecular, cellular, and systems-level processes. At molecular levels, meditation affects gene expression, neurotransmitter systems, and neurotrophic factors including brain-derived neurotrophic factor, or BDNF, that supports neuronal survival and growth. At cellular levels, meditation might enhance neurogenesis, synaptogenesis, dendritic arborization, and myelination. At systems levels, meditation alters functional connectivity and network dynamics. Integrating across these levels would provide comprehensive mechanistic understanding. Animal models allow mechanistic investigation impossible in humans, but face the challenge that meditation involves intentional mental states difficult or impossible to induce in animals. However, some meditation components, including focused attention and stress reduction, might be modeled. For example, training animals to sustain attention on specific stimuli while ignoring distractions parallels focused attention meditation. Stress reduction interventions in animals could model meditation's stress buffering effects. Such models enable cellular and molecular investigation of potential mechanisms. Biomarkers predicting meditation response would allow personalizing practice recommendations. Some evidence suggests baseline brain activity, connectivity patterns, or genetic variants predict who benefits most from meditation training. For example, individuals with higher baseline DMN connectivity might show greater DMN reduction with practice. Genetic variants affecting serotonin or dopamine systems might influence response. Validating and extending these preliminary findings could enable precision meditation prescription. The relationship between meditation and psychedelic experiences is receiving renewed attention. Both meditation and psychedelics can produce profound alterations in consciousness, including ego dissolution, mystical experiences, and lasting changes in outlook. Some preliminary research suggests psychedelics might facilitate meditation learning by providing direct experience of altered states meditation cultivates gradually. However, combining psychedelics and meditation raises safety and ethical concerns, requiring careful consideration. Compassion and loving-kindness meditation deserve particular emphasis, given evidence for specific prosocial effects beyond general mindfulness. These practices explicitly cultivate positive emotions towards self and others, whereas mindfulness emphasizes non-reactive awareness. Studies find compassion training enhances helping behavior, reduces implicit bias, increases charitable giving, and improves relationship quality. The neural basis involves empathy networks, reward circuits responding to others' well-being, and perhaps oxytocin system modulation. Oxytocin, a neuropeptide involved in social bonding, trust, and affiliation, might mediate compassion meditation effects. Some studies find increased oxytocin following loving-kindness meditation, though findings are inconsistent. If replicated, oxytocin elevation could contribute to prosocial effects by enhancing attention to social cues, increasing trust, and promoting affiliative motivation. However, oxytocin effects are complex and context-dependent, so simplistic interpretations should be avoided. Social connection and loneliness profoundly affect health. Loneliness increases mortality risk comparable to smoking. Meditation might reduce loneliness through multiple pathways, including reduced self-focused rumination, making social interactions more rewarding, enhanced empathy, and compassion improving relationship quality, reduced social anxiety facilitating social approach, and biological effects on inflammatory pathways affected by loneliness. Studies find mindfulness and compassion training reduce loneliness, though mechanisms require further investigation. Meditation in special populations including prisoners, veterans, and homeless individuals shows promise for addressing trauma, reducing aggression and recidivism, and improving mental health in underserved groups. Prison meditation programs find reduced hostility, improved impulse control, and lower recidivism rates. Veteran programs find reduced PTSD symptoms and improved emotion regulation. These applications demonstrate meditation's potential beyond affluent populations, but require culturally sensitive implementation and evaluation. Workplace meditation programs are increasingly common as employers seek to reduce stress and enhance productivity. Research finds workplace meditation programs reduce stress, improve job satisfaction, and enhance task performance and decision-making. However, concerns exist about using meditation to help workers accept exploitative conditions rather than addressing workplace stressors. Ethical implementation requires genuine organizational commitment to well-being beyond productivity gains. Educational applications of meditation, particularly mindfulness programs in schools, aim to improve attention, emotion regulation, and stress resilience in students. Programs show benefits including reduced anxiety, improved grades and test scores, better classroom behavior, and enhanced social-emotional skills. However, implementation challenges include teacher training, curriculum integration, and ensuring age-appropriate practices. Research is needed on long-term outcomes and optimal implementation. Athletic performance enhancement through meditation capitalizes on improved attention, reduced performance anxiety, and enhanced mind-body awareness. Elite athletes in various sports increasingly incorporate meditation into training. Research finds meditation improves reaction time, reduces competitive anxiety, enhances flow states during competition, and speeds recovery. The mechanisms likely include optimized arousal levels, enhanced attention to task-relevant cues, and reduced interference from performance-irrelevant thoughts. Creativity and meditation show complex relationships. Some research suggests meditation enhances divergent thinking, generating multiple creative solutions, while other studies find meditation enhances convergent thinking, identifying the single correct solution. Open monitoring meditation might enhance creativity by reducing cognitive rigidity and habitual response patterns, allowing novel associations. However, meditation might reduce creativity if practices emphasize focused attention on single objects rather than exploratory cognition. The default mode network's role in creativity complicates predictions. The DMN supports imagination, mental simulation, and spontaneous thought, processes relevant to creativity. If meditation reduces DMN activity, might it reduce creativity? However, meditation might enhance creativity by modulating rather than simply suppressing DMN activity, allowing creative cognition while reducing unproductive rumination. Distinguishing constructive from unconstructive DMN activity is a frontier for meditation neuroscience. Meditation traditions describe stages of practice with progressively deepening effects. Initial stages focus on ethical conduct and basic concentration. Intermediate stages develop sustained attention and insight into mental processes. Advanced stages involve profound alterations in consciousness and self-understanding. Scientific investigation has primarily studied early stages. Understanding advanced stages requires partnership with highly experienced practitioners and may reveal human capacities not well captured by current neuroscience. The jhanas, absorption states described in Buddhist meditation texts, involve deep concentration with progressive reduction of sensory processing and thought. First jhana combines concentration with pleasant sensations and limited thought. Higher jhanas involve fading of thought and sensations, until the eighth jhana involves neither perception nor non-perception. Modern practitioners have learned to reliably enter jhanic states, and preliminary neuroscience studies reveal distinctive brain activity, including increased alpha and theta and decreased sensory processing. Insight practices aim to investigate the nature of experience, revealing the constructed nature of perceptual and cognitive processes. Vipassana, or insight meditation, involves sustained observation of bodily sensations, emotions, and thoughts, noticing their arising and passing. Practitioners report experiencing the three characteristics: impermanence, unsatisfactoriness, and no self. Scientific investigation of insight meditation is limited, but might reveal how metacognitive observation of mental processes changes their subjective character. The role of ethics in meditation practice is emphasized in traditional contexts, but often minimized in modern secular applications. Traditional systems teach ethical conduct, non-harming, truthfulness, not stealing, appropriate sexual behavior, avoiding intoxicants, as foundations for meditation. Ethics might facilitate meditation by reducing guilt and regret that disturb concentration, aligning behavior with values, reducing internal conflict, and creating social conditions supportive of practice. Research on ethics meditation relationships is sparse but important. Wisdom, the ultimate goal in many meditation traditions, refers to direct understanding of reality, transcending conceptual knowledge. Wisdom traditions distinguish between intellectual understanding, knowing about something, and experiential wisdom, directly realizing something through practice. Meditation aims to cultivate experiential wisdom about mind, self, and reality. How such wisdom relates to scientific knowledge, and whether it can be investigated scientifically, are profound questions at the intersection of science and contemplation. The relationship between science and meditation raises epistemological questions. Science uses third-person observation and measurement. Meditation uses first-person introspection and phenomenological investigation. Can these approaches be integrated, or do they access fundamentally different kinds of knowledge? Contemplative science attempts integration by training scientists in meditation and meditators in neuroscience, creating bilingual researchers who can translate between experiential and scientific languages. The future of meditation research will likely involve larger-scale studies with better controls, longer follow-up periods tracking sustained effects, investigation of mechanisms at multiple biological levels from genes to networks, identification of individual difference factors predicting response, comparison of different meditation types and traditions, and collaboration with experienced practitioners to investigate advanced practices. Computational modeling of meditation's neural mechanisms could integrate disparate findings into coherent frameworks. Clinical translation of meditation research faces challenges, including training therapist clinicians in meditation competency, developing quality assurance for meditation instruction, determining how to match patients to practices, integrating meditation with other treatments, and managing adverse effects. Successful translation requires not just evidence of efficacy, but practical implementation strategies, reimbursement mechanisms, and integration into treatment guidelines. Progress on these fronts continues, but work remains. Meditation as public health intervention could potentially address epidemic stress, anxiety, and depression, but implementation at population scale presents enormous challenges. School-based programs reach millions of children. Workplace programs reach adults. App-based meditation provides scalable delivery. However, ensuring quality, supporting adherence, reaching disadvantaged populations, and evaluating population-level impacts require substantial investment and innovation. The neurobiology of breathing in meditation reveals intricate connections between respiration, brain rhythms, and emotional states. Breathing occupies a unique position in meditation practice, serving as both the most common meditation object and a bidirectional bridge between voluntary and involuntary physiological processes. Unlike heartbeat or digestion, breathing can be consciously controlled or allowed to proceed automatically. This dual nature makes breath an ideal focus for cultivating awareness of the boundary between voluntary and involuntary processes, and for learning to influence typically automatic functions. The respiratory rhythm generator in the brainstem, specifically the pre-Bötzinger complex and parafacial respiratory group, produces the basic breathing pattern without conscious input. This network generates rhythmic bursts of activity driving inspiratory and expiratory muscle contractions. The pattern adapts automatically to metabolic demands through chemoreceptor feedback, detecting blood carbon dioxide, oxygen, and pH. However, cortical regions, including motor cortex and premotor areas, can override brainstem control during voluntary breathing or speech. Neural coupling between breathing and brain oscillations has been documented across multiple regions and frequency bands. In the olfactory bulb, respiration entrains neural oscillations. Neurons fire in phase with breathing cycles. This respiratory-locked activity propagates to olfactory cortex, hippocampus, amygdala, and prefrontal cortex. Studies using intracranial electrodes in epilepsy patients reveal that breathing rhythm modulates neural activity in limbic and cortical areas, with effects varying by breathing phase, inhalation versus exhalation. The functional consequences of respiratory brain coupling are beginning to be understood. Cognitive performance on memory and attention tasks varies with breathing phase. Fear processing in the amygdala differs between inhalation and exhalation. Emotional face recognition is enhanced during inhalation through nasal breathing, but not mouth breathing, suggesting nasal airflow mechanoreceptors contribute to coupling. These findings indicate breathing doesn't just reflect, but actively modulates cognitive and emotional processing. Meditation practices modifying breathing patterns may therefore influence brain function through multiple mechanisms beyond simple oxygenation. Slow breathing at resonance frequency, approximately 6 breaths per minute for most adults, maximizes heart rate variability and baroreflex sensitivity, optimizing cardiovascular respiratory coupling. This breathing rate enhances vagal tone and parasympathetic dominance. Many meditation traditions naturally slow breathing to this range, potentially contributing to stress reduction and autonomic regulation. Breath-holding practices like kumbhaka in yoga produce distinct physiological effects, including transient hypoxia and hypercapnia, low oxygen, and high carbon dioxide. These conditions activate peripheral chemoreceptors, triggering sympathetic activation initially, but prolonged practice may recalibrate chemoreceptor sensitivity, increasing tolerance for carbon dioxide. Some practitioners can maintain breath holds for minutes, demonstrating extreme voluntary control over normally involuntary respiratory drive. Alternate nostril breathing, or nadi shodhana, involves breathing through one nostril at a time in alternating pattern. Preliminary studies suggest this practice influences autonomic balance and hemispheric brain activity, with right nostril breathing associated with increased sympathetic activity and left hemisphere activation, while left nostril breathing shows opposite patterns. However, findings are inconsistent and mechanisms unclear. Whether effects result from differential airflow, attention, or other factors remains unknown. The psychological significance of breath in meditation extends beyond physiology. Breath serves as a constantly available present moment anchor. Unlike external objects that may be absent, breathing always occurs in the present. Breath provides a neutral focus, less emotionally charged than thoughts or body sensations, allowing practitioners to stabilize attention. Breath's rhythmic nature, the repetitive cycle of inhalation and exhalation, facilitates concentration through predictable periodicity. Breath awareness practices vary in specific instructions and emphasis. Some practices direct attention to sensations at the nostrils, the touch of air entering and leaving. Others focus on abdomen movements, the rising and falling with breath. Still others attend to the whole body breathing, the expansion and contraction of the entire torso. Different focal points may recruit different neural networks and produce different experiential qualities, though systematic comparison is limited. The counting of breaths, used in some meditation traditions, adds a cognitive task to breath awareness. Practitioners count sequential breaths from 1 to 10, then repeat, or count only exhalations. This requires maintaining both breath awareness and numerical tracking, engaging working memory and executive attention. Losing count signals mind wandering, providing immediate feedback. Studies find breath counting correlates with reduced mind wandering, suggesting it strengthens attention more than simple breath awareness. Natural breathing versus controlled breathing represents an important distinction in meditation instructions. Some traditions emphasize observing breathing as it naturally occurs without attempting to control rate, depth, or rhythm. This cultivates equanimity and acceptance of present experience. Other traditions prescribe specific breathing patterns, slow, deep, or rhythmic breathing. The former emphasizes awareness development, while the latter combines awareness with physiological regulation through breathing manipulation. The breath body or breath sensation body, the pattern of sensations throughout the torso associated with breathing, serves as an expanded breath awareness object. Practitioners attend to the wave of sensations spreading through chest, abdomen, back, and shoulders with each breath. This distributed attention may recruit broader somatosensory networks than focal attention to nostrils or abdomen. The breath body practice bridges attention to a specific object and open monitoring of changing sensations. Breathing and emotion regulation show bidirectional relationships. Emotional states alter breathing patterns. Anxiety produces rapid, shallow breathing. Calm produces slow, deep breathing. Conversely, voluntarily adopting breathing patterns associated with specific emotions can induce those emotional states. This suggests breathing serves as both consequence and cause of emotional states, providing a pathway for voluntary emotion regulation. Meditation training in breath awareness may enhance sensitivity to breathing emotion relationships, improving emotion regulation. The subjective experience of breathing changes with meditation practice. Novices report that focusing on breath feels effortful, boring, or anxiety-provoking. The breath may feel unnatural when observed, or attention repeatedly drifts. With practice, breath awareness becomes more effortless and stable. Advanced practitioners report that breath sensations become vivid, subtle details emerge, and breath seems to permeate consciousness. The phenomenological transformation of simple breath awareness illustrates how meditation changes the quality of experience. Breathwork practices extending beyond traditional meditation have gained popularity, including holotropic breathwork, Wim Hof method, and transformational breath. These practices often involve hyperventilation, producing altered states through hypocapnia, low blood carbon dioxide. Hypocapnia causes cerebral vasoconstriction, reducing brain blood flow, potentially contributing to altered consciousness. The relationship between these intensive breathwork practices and traditional meditation remains unclear, with different aims and mechanisms likely involved. The role of carbon dioxide in breathing regulation and meditation deserves more attention. Rising carbon dioxide is the primary stimulus driving breathing, not low oxygen. The discomfort during breath holding or slow breathing largely results from carbon dioxide accumulation, triggering air hunger. Meditation training may increase tolerance for elevated carbon dioxide, reducing air hunger distress. This could contribute to the calm acceptance of uncomfortable sensations cultivated in meditation. breathing pattern variability, the natural fluctuation in respiratory rate, depth, and rhythm, may serve as a marker of autonomic flexibility. Greater variability indicates responsive regulation adapting to changing conditions. Some evidence suggests meditation increases breathing pattern variability, though findings are limited. If meditation enhances natural breathing variability while reducing overall rate, this would suggest optimized rather than simply reduced breathing. Sighing, an involuntary deep breath occurring approximately every 5 minutes in normal breathing, serves physiological functions, including re-expanding alveoli and regulating arousal. Sigh frequency increases with stress and anxiety. Meditation practice might normalize sigh frequency, though this hasn't been systematically studied. Practitioners sometimes note that meditation sessions include spontaneous deep breaths or sighs, which might represent shifts in arousal or tension release. The breath as a metaphor extends throughout meditation literature, breath representing impermanence as each breath arises and passes, breath representing life itself as breathing sustains existence, breath representing the present moment as breath only exists now. These metaphorical meanings enrich meditation practice beyond simple attention training, connecting breathing to broader philosophical and existential themes. The phenomenological and symbolic significance of breath in meditation may contribute to effects beyond physiological mechanisms. Contemplative practices across diverse traditions share common elements while differing in specific techniques, cultural contexts, and philosophical frameworks. Meditation is not unique to Buddhism or even to Asian traditions. Contemplative practices exist in virtually every major religious and philosophical tradition, suggesting they address universal human needs or capacities. Examining meditation across traditions reveals both common features suggesting shared mechanisms and unique elements reflecting different goals, worldviews, and cultural contexts. Understanding this diversity enriches scientific investigation and practical application. Christian contemplative traditions include practices like Lectio Divina, sacred reading involving meditative reflection on scripture, centering prayer, resting in silent awareness of God's presence, and the Jesus Prayer, repetitive recitation of a short prayer phrase. These practices share features with Buddhist meditation, including sustained attention, repetition, and cultivation of specific mental states. However, their explicitly theistic content and devotional aims differ from Buddhist non-theistic approaches, emphasizing insight into mind and reality. The similarities between Christian contemplation and Buddhist meditation have led to interfaith dialogue and practice integration. Contemplative outreach programs teach meditation techniques drawn from Buddhist sources to Christian audiences, framing practices in terms compatible with Christian theology. Some Christian practitioners find Buddhist techniques enhance their prayer life and spiritual development. However, theological differences remain. Buddhist meditation aims for liberation from suffering through wisdom, while Christian contemplation seeks union with the divine through grace. Islamic Sufism includes contemplative practices such as dhikr, repetitive recitation of divine names or phrases, muraqabah, meditation focusing attention on the heart or divine presence, and whirling as practiced by Mevlevi dervishes, producing altered states through prolonged spinning. These practices combine devotional elements with attention training and consciousness exploration. The emphasis on remembrance of God and purification of the heart reflects Islamic theological commitments while sharing attention and presence cultivation with other traditions. Jewish meditation traditions, though less widely known than Buddhist or Christian practices, include hitbodut, secluded contemplation and spontaneous prayer, Kabbalistic visualizations of divine emanations and Hebrew letters, and contemplative Torah study. Hasidic traditions emphasize devekut, cleaving to God through sustained divine awareness during daily activities. These practices integrate meditation with Jewish theological frameworks, emphasizing covenant, law, and relationship with a personal God. Hindu meditation traditions encompass enormous diversity, including Jnana yoga, emphasizing wisdom and self-inquiry, Bhakti yoga, emphasizing devotion and emotional connection to the divine, Karma yoga, emphasizing selfless action, and Raja yoga, codified in Patanjali's Yoga Sutras, emphasizing systematic eight-limbed practice culminating in samadhi. The philosophical frameworks include non-dual Advaita Vedanta, seeing reality as unified consciousness, dualistic schools seeing individual souls distinct from God, and tantric approaches transforming rather than transcending embodied existence. Yoga, as practiced in modern Western contexts, typically emphasizes physical postures or asanas, with some breathing practices and brief meditation. This represents only one limb of Patanjali's eight-limbed path, which also includes ethical observances, breath control, sense withdrawal, concentration, meditation, and absorption. Traditional yoga is comprehensive spiritual practice aiming for liberation, though this context is often lost in modern fitness-oriented adaptations. The relationship between physical yoga and meditation deserves investigation. Does asana practice enhance meditation? And if so, through what mechanisms? Taoist meditation includes practices like zhuang, or sitting and forgetting, letting go of conceptual thought and bodily sensation, niguan or inner observation, turning attention inward to observe qi or life energy flow, and various breathing and visualization practices aimed at cultivating and circulating vital energy. Taoist practices emphasize naturalness, spontaneity, and harmony with the Tao, the underlying principle of reality. This contrasts with more effortful Buddhist practices while sharing emphasis on present awareness and letting go of attachments. Indigenous traditions worldwide include contemplative practices often embedded in rituals, vision quests, and connection with nature. These practices may involve prolonged solitude, fasting, sensory deprivation, or use of sacred plants producing altered consciousness. While differing significantly from Asian meditation traditions in form and context, they share aims of self-knowledge, connection with sacred or transpersonal dimensions, and transformation of consciousness. Scientific study of indigenous practices requires cultural sensitivity and partnership with communities. Secular mindfulness, as taught in MBSR and related programs, deliberately strips traditional Buddhist meditation of religious and philosophical content to increase accessibility and avoid establishment clause concerns in public settings. This secularization has benefits including reaching wider audiences and facilitating research with mainstream populations. However, critics argue that decontextualized mindfulness loses ethical grounding, risks commodification, and may not produce the deep transformations traditional practice aims for. The debate over secular versus traditional meditation raises important questions. Is meditation's effectiveness dependent on traditional contexts, including ethics, community, and philosophical frameworks? Or are the core techniques universally effective regardless of cultural packaging? Can meditation be effectively transmitted through apps and brief courses? Or does it require sustained teacher-student relationships and immersion in practice communities? These questions have both pragmatic implications for how meditation is taught and philosophical implications for understanding meditation's nature. Movement-based contemplative practices, including Tai Chi, Qigong, and walking meditation, combine physical activity with meditative awareness. These practices may be more accessible than seated meditation for individuals with physical limitations or high energy levels. Research finds movement meditation produces some similar benefits to seated meditation, including stress reduction and improved attention, though direct comparisons are limited. The combination of physical and mental training might provide unique benefits not achievable through purely mental or physical practice alone. Sound-based practices, including mantra repetition, chanting, and listening meditation, use auditory objects for attention focus. Mantra meditation involves silent or vocalized repetition of words or phrases, with different traditions using different mantras. The rhythmic, repetitive nature of mantra practice may facilitate concentration through entrainment of attention to regular cycles. Brain imaging during mantra meditation shows deactivation of language areas despite internal verbalization, suggesting processing differs from ordinary self-talk. Visualization practices common in Tibetan Buddhism and Hindu Tantra involve constructing detailed mental images of deities, mandalas, or other complex forms, and maintaining sustained attention on these visualizations. These practices develop concentration and imagination while carrying symbolic and devotional significance. The neural mechanisms of visualization meditation likely differ from breath awareness, recruiting visual imagery networks. Whether visualization practices produce unique brain changes compared to non-visual meditation deserves investigation. The role of ritual in contemplative practice varies across traditions, but often provides structure, meaning, and community support. Rituals may include prostrations, offerings, circumambulation of sacred sites, or liturgical recitations. While not meditation per se, rituals create context supporting practice and express commitments and values. Secular meditation typically minimizes ritual, but some structure, lighting candles, ringing bells, or formal sitting positions, may enhance practice by signaling transitions into meditative states. Teacher-student relationships in traditional meditation contexts provide instruction, feedback, guidance through difficulties, and inspiration. Teachers assess student progress, adapt instructions to individual needs, and embody the attainment students aspire toward. The importance of teachers varies across traditions and individuals. Some emphasize complete reliance on teachers, others encourage independent practice. Modern meditation often reduces teacher contact, raising questions about optimal instruction models, balancing guidance with autonomy. Retreat practice involving intensive meditation over days, weeks, or months is common across contemplative traditions. Retreats provide extended periods of practice with minimal external distractions, allowing deeper concentration and insights than daily practice permits. The intensive format produces both opportunities, rapid progress, profound experiences, and risks, physical discomfort, psychological difficulties, adverse effects. Research on retreat practice could clarify dose-response relationships and identify factors determining whether intensive practice benefits or harms participants. The relationship between meditation and prayer deserves consideration, particularly regarding brain mechanisms. Both involve sustained attention, specific mental content, and cultivation of particular states like devotion or compassion. Brain imaging during prayer shows activation patterns overlapping with but also distinct from meditation, suggesting partially shared mechanisms. Prayer typically involves personal relationship with a divine other, while meditation often emphasizes impersonal awareness, potentially recruiting different social cognition and theory of mind networks. The molecular and cellular mechanisms underlying meditation's effects on the brain and body are beginning to be elucidated through genetic, epigenetic, and biochemical research. While neuroimaging reveals large-scale brain changes with meditation, understanding requires investigation at molecular and cellular levels, where the fundamental mechanisms of neuroplasticity operate. Recent research has begun examining how meditation affects gene expression, neurotransmitter systems, neurotrophin levels, and cellular signaling pathways. These molecular changes likely underlie the structural and functional brain changes observed at systems level. Brain-derived neurotrophic factor, or BDNF, a protein supporting neuron survival, growth, and synaptic plasticity, shows increased expression following meditation training in several studies. BDNF binds TRK-B receptors on neurons, activating intracellular signaling cascades, including the MAPK and Pi3K AKT pathways that promote dendritic growth, synapse formation, and long-term potentiation. Exercise robustly increases BDNF, contributing to its cognitive benefits. If meditation similarly increases BDNF, this could mediate structural brain changes, including hippocampal volume increases. The mechanisms by which meditation might increase BDNF are speculative, but could include reduced stress hormone exposure. Cortisol suppresses BDNF expression, enhanced arousal and attention, moderate norepinephrine levels promote BDNF, or direct effects of meditation-altered neural activity on BDNF transcription. BDNF has activity-dependent expression. Neurons active in learning and memory increase BDNF production. If meditation involves learning and neural plasticity, this might drive BDNF upregulation. Nerve growth factor, or NGF, another neurotrophin supporting neuron survival and function, has been examined in meditation research with mixed findings. Some studies find increased NGF following meditation, others find no change. The variability might reflect differences in meditation type, dose, population, or measurement methods. If meditation does increase NGF, mechanisms might parallel BDNF, including stress reduction and activity-dependent expression. NGF supports cholinergic neurons important for attention and memory, suggesting potential mechanisms for cognitive benefits. Neurotransmitter systems show modulation by meditation, though findings are often inconsistent across studies. Serotonin, involved in mood regulation, shows increased metabolites in some meditation studies, suggesting increased synthesis or release. Enhanced serotonin function could contribute to antidepressant and anxiolytic effects of meditation. However, direct measurement of brain serotonin in humans is not possible. Studies typically measure peripheral metabolites or use PET imaging with serotonin receptor ligands, providing only indirect evidence. Dopamine, critical for reward, motivation, and attention, shows increased release in ventral striatum during meditation in one PET study using raclopride displacement to infer dopamine release. This suggests meditation may be intrinsically rewarding, potentially contributing to sustained practice motivation. Enhanced dopamine function could also improve attention and working memory. However, replication is needed given single-study findings and the limitations of PET imaging for inferring neurotransmitter dynamics. GABA, the main inhibitory neurotransmitter, shows increased brain levels measured by magnetic resonance spectroscopy following yoga and meditation practice in some studies. Enhanced GABA could contribute to anxiety reduction and improved emotion regulation. GABA levels correlate inversely with anxiety symptoms. However, magnetic resonance spectroscopy measures total GABA pools, not synaptic GABA or receptor binding, limiting mechanistic interpretation. Animal studies could clarify whether meditation-type interventions alter GABA synthesis, release, or receptor expression. The endocannabinoid system, involved in stress regulation, reward, and pain modulation, might be affected by meditation, though research is extremely limited. Endocannabinoids are lipid neurotransmitters binding cannabinoid receptors, producing effects including stress reduction and altered time perception. Exercise increases endocannabinoid levels, contributing to runner's high. If meditation similarly affects endocannabinoids, this could contribute to stress reduction and altered consciousness. However, this remains entirely speculative without supporting data. Epigenetic modifications, chemical changes to DNA or histones affecting gene expression without altering DNA sequence, represent a mechanism linking experience to lasting biological changes. Meditation training has been associated with epigenetic changes in genes involved in inflammation, stress response, and neuroplasticity. For example, one study found altered methylation patterns in genes regulating inflammation and stress after mindfulness training. Epigenetic changes could mediate long-lasting effects of meditation that persist after practice cessation. The specific epigenetic modifications observed include DNA methylation, addition of methyl groups to cytosine bases, and histone modifications, including acetylation and methylation, affecting DNA accessibility. These modifications can increase or decrease gene expression, altering cellular function. Environmental experiences including stress, diet, and learning produce epigenetic changes. If meditation induces beneficial epigenetic modifications, this could explain how relatively brief interventions produce lasting effects. Mitochondrial function, critical for cellular energy production, might be enhanced by meditation through stress reduction and parasympathetic activation. Chronic stress impairs mitochondrial function, reducing ATP production and increasing oxidative stress. If meditation reduces stress, mitochondria might function more efficiently. Some preliminary evidence suggests meditation practitioners have better preserved mitochondrial function with aging, though research is limited. Enhanced mitochondrial function could contribute to improved energy, cognitive function, and healthy aging. Oxidative stress, resulting from imbalance between reactive oxygen species production and antioxidant defenses, contributes to aging and disease. Chronic stress increases oxidative stress. Meditation training has been associated with reduced oxidative stress markers and increased antioxidant enzyme activity in some studies. Reduced oxidative stress could contribute to benefits including slower cellular aging, reduced inflammation, and better cardiovascular health. Mechanisms might include reduced stress hormone exposure and enhanced antioxidant gene expression. Autophagy, the cellular process degrading and recycling damaged proteins and organelles, maintains cellular health and is upregulated by stress, including caloric restriction and exercise. Whether meditation affects autophagy is unknown, but if meditation mimics other health span extending interventions, autophagy enhancement is plausible. Autophagy declines with aging, contributing to accumulation of cellular damage. Enhancing autophagy through meditation could potentially slow cellular aging, though this remains entirely speculative. Heat shock proteins, or HSPs, molecular chaperones helping proteins fold correctly and protecting against stress, show increased expression in response to various stressors including heat, oxidative stress, and psychological stress. Some evidence suggests meditation affects HSP expression, though findings are limited and mixed. HSPs protect against cellular stress and support neuroplasticity. If meditation upregulates beneficial HSPs, this could enhance stress resilience at cellular levels. Sirtuins, a family of proteins involved in cellular metabolism, stress resistance, and aging, are activated by caloric restriction and exercise, contributing to health span extension in animal models. Whether meditation affects sirtuin activity is unknown, but represents an interesting possibility given meditation's overlap with other health span extending interventions. Sirtuins require NAD+ as cofactor, linking them to cellular energy metabolism. If meditation affects cellular energy homeostasis, this might influence sirtuin activity. The gut-brain axis, bidirectional communication between gut and brain via neural, hormonal, and immune pathways, might be affected by meditation. The vagus nerve connects gut and brain, carrying signals in both directions. Meditation enhances vagal tone, potentially affecting gut function. The gut microbiome produces neurotransmitters and metabolites affecting brain function. If meditation alters gut microbiome composition or function, this could contribute to mental health effects through gut-brain signaling. Inflammation at molecular levels involves transcription factors like NF-kappa be activating pro-inflammatory gene expression. As mentioned earlier, meditation reduces CTRA gene expression profiles characterized by elevated NF-kappa B-mediated inflammatory genes. The molecular mechanisms by which meditation affects gene expression could involve glucocorticoid receptor signaling. Cortisol binds receptors that modulate transcription factor activity. Beta-adrenergic signaling, sympathetic neurotransmitters activate signaling affecting gene expression. Or vagal anti-inflammatory pathways, parasympathetic signaling inhibits inflammatory gene expression. MicroRNAs, small non-coding RNAs regulating gene expression post-transcriptionally, represent another potential mechanism. MicroRNAs bind messenger RNAs, preventing their translation into proteins. Stress and inflammation alter microRNA expression profiles. Preliminary research suggests meditation might affect microRNA expression, potentially contributing to lasting effects on gene expression and cellular function. However, research is in very early stages and findings require replication and mechanistic clarification. The blood-brain barrier, which tightly regulates what substances can enter brain from blood, might be affected by meditation through stress and inflammation pathways. Chronic stress and inflammation can increase blood-brain barrier permeability, potentially allowing harmful substances into brain. If meditation reduces stress and inflammation, this might preserve blood-brain barrier integrity, protecting brain health. However, this possibility hasn't been directly investigated. Neuroinflammation, inflammation within the brain involving activated microglia and astrocytes, contributes to neurodegenerative diseases and depression. If meditation reduces peripheral inflammation, might it also reduce neuroinflammation? Animal studies show that stress reduction interventions can reduce microglial activation. If meditation has similar effects in humans, this could contribute to neuroprotection and mental health benefits, though direct evidence is lacking. The molecular clock genes regulating circadian rhythms might be affected by meditation, given meditation's effects on sleep and circadian patterns. Clock genes including clock, BMAL1, PER, and cry form transcriptional translational feedback loops generating approximately 24-hour rhythms. Disrupted circadian rhythms contribute to metabolic and mental health problems. If meditation helps normalize circadian gene expression, this could contribute to improved sleep and metabolic health. Advanced meditation states and the frontiers of contemplative neuroscience reveal phenomena challenging current understanding of consciousness and human potential. While most meditation research examines novice practitioners or early-stage practice, traditional contemplative systems describe advanced states and stages requiring years or decades of intensive practice. These include absorption states called jhanas, insight experiences revealing the nature of mind and reality, and purported capacities, including voluntary control of typically involuntary functions. Scientific investigation of advanced meditation is in its infancy, but may reveal human capacities unexplored by mainstream neuroscience and psychology. The jhanas or dhyanas represent a systematic progression of meditative absorption states characterized by decreasing sensory processing, conceptual thought, and eventually even the sense of pleasure that characterizes lower jhanas. Traditional texts describe 8 or 9 jhanas with increasingly subtle qualities. First jhana involves sustained attention on a meditation object accompanied by pleasant sensations, joy, and some discursive thought. Second jhana involves fading of discursive thought while sustaining pleasant sensations and joy. Higher jhanas involve progressive simplification of experience. Third jhana retains equanimous contentment without the rapture of earlier jhanas. Fourth jhana involves neutral feeling tone without pleasure, pain, or strong affect. Formless jhanas transcend bodily sensations and perceptions. The fifth jhana is boundless space. Sixth is boundless consciousness. Seventh is nothingness. And eighth is neither perception nor non-perception. These descriptions suggest profound alterations of consciousness not typically studied in laboratory settings. Modern practitioners, particularly those trained in Theravada Buddhist traditions emphasizing jhana development, can reliably enter and exit these states on demand. Preliminary neuroscience studies of jhana meditators using EEG and fMRI reveal distinctive patterns. First jhana shows increased frontal gamma and theta with decreased sensory processing. Higher jhanas show progressive decreases in DMN activity, sensory cortex activity, and eventually very low amplitude, very high frequency gamma suggesting minimal information processing. However, samples are small and interpretations provisional. The question of whether jhanas represent states inaccessible to non-meditators or simply unusual configurations of universal neural processes remains open. Some researchers suggest jhanas might be achieved through neurofeedback training without meditation. testing whether the subjective qualities emerge from specific brain states, regardless of how those states are induced. Others argue jhanas require not just brain states, but also the interpretive frameworks and progressive training meditation provides, making them irreducible to neural patterns. Cessation, or nirodha samapatti, represents an even more extreme state described in Buddhist texts, complete cessation of consciousness and mental activity for minutes to hours. Practitioners report experiencing nothing, no time passage, no awareness, yet they reliably emerge after intended durations. This state seemingly contradicts the idea that awareness is always present. If cessation truly involves complete unconsciousness, what brain states allow complete activity cessation while maintaining life functions and reliable reemergence? No published neuroscience studies have examined cessation, likely due to extreme rarity of practitioners who can enter this state. Hypothetically, cessation might involve profound cortical deactivation while preserving brainstem functions, maintaining breathing and heartbeat. Comparing cessation to coma, general anesthesia, or deep sleep could clarify unique features. Whether cessation has any functional benefits or represents simply an extreme but functionally meaningless state remains unknown. Non-dual awareness, described across contemplative traditions, involves loss of subject-object duality. The sense of being a subject observing objects of experience dissolves into undivided awareness. Practitioners describe not experiencing from a location or perspective, or that consciousness itself becomes the totality of experience without an experiencer. Neuroscience of non-dual awareness is challenging because the state is difficult to maintain while performing tasks or responding to stimuli typically used in brain imaging. Preliminary studies using EEG during reports of non-dual awareness find patterns including increased posterior gamma, decreased frontal parietal connectivity, suggesting reduced executive control, and altered alpha band connectivity. Subjective reports emphasize vast spaciousness, luminous clarity, and complete lack of self-sense. Whether these reports describe genuine alterations in consciousness structure or merely unusual interpretations of normal experience is debated. First-person phenomenological investigation combined with neuroscience might clarify the nature of non-dual states. Insight experiences, or vipassana jnanas in Buddhist terminology, involve recognizing the three characteristics of experience: impermanence, unsatisfactoriness, and not self. These are not merely intellectual understandings, but direct perceptions fundamentally transforming how experience is interpreted. Advanced practitioners report perceiving the rapid arising and passing of sensations, thoughts, and consciousness itself, revealing the constructed nature of seemingly continuous experience. The phenomenology of insight experiences is rich and diverse. Practitioners describe seeing thoughts arise spontaneously without an author, experiencing the body as a collection of sensations without a unified self, or recognizing suffering as inherent in clinging to impermanent experiences. These insights purportedly reduce attachment, suffering, and the sense of separate selfhood. Whether such experiences produce lasting transformation and how they relate to brain function are important questions for contemplative neuroscience. The dark night of contemplative practice, described across traditions, involves difficult phases where practice intensifies challenging mental states before subsequent breakthroughs. These phases might include increased anxiety, depression, perceived dissolution of reality, or disturbing sensory experiences. Some traditions view these as necessary stages, while others see them as signs of misguided practice. Understanding these phenomena is important for ensuring meditation's safety and providing appropriate support. Recent attention to meditation-related adverse effects has revealed that challenging experiences are not rare. The Varieties of Contemplative Experience study has collected detailed accounts of difficult meditation experiences, finding themes including fear, anxiety, disintegration of self-concept, changes in perception, and more. Most experiences resolved without lasting harm, but some resulted in persistent difficulties requiring professional help. Determining who is at risk for adverse effects and how to prevent or manage them is crucial for responsible meditation teaching. Voluntary control of autonomic functions represents another domain where advanced practitioners may demonstrate unusual capacities. Reports describe yogis controlling heart rate, body temperature, or metabolism, functions normally beyond voluntary control. While some claims are exaggerated or fraudulent, verified cases exist, including Wim Hof demonstrating resistance to cold and voluntary immune suppression. Understanding mechanisms could reveal neuroplastic potential generally unexplored. Tummo, or inner heat practice in Tibetan Buddhism, involves meditation combined with breathing exercises purportedly generating body heat, allowing practitioners to meditate in extreme cold wearing minimal clothing. Scientific studies of Tummo practitioners find increased body temperature and metabolism during practice, validating subjective reports. The mechanisms likely involve sympathetic activation combined with muscular thermogenesis through shivering or tension. Whether Tummo has applications beyond extreme cold tolerance remains unclear. Reports of prolonged periods without food or water by certain yogis, if valid, would challenge physiological understanding. However, such claims are difficult to verify rigorously, and extraordinary claims require extraordinary evidence. Careful observation of practitioners under controlled conditions is needed but rarely conducted. Most such cases likely involve exaggeration, deception, or covert consumption. Still, the question of whether intensive meditation alters metabolic requirements deserves investigation with proper controls. Lucid dreaming, conscious awareness during dreaming with recognition that one is dreaming, is cultivated in some meditation traditions, including Tibetan dream yoga. Lucid dreamers can voluntarily control dream content and use dreams for practice. Neuroscience finds lucid dreaming involves prefrontal cortex reactivation during REM sleep, the regions suppressed in normal dreams. Meditation training is associated with increased lucid dreaming frequency, suggesting meditation-enhanced meta-awareness carries over into sleep. Out-of-body experiences and boundary dissolution, sometimes reported during meditation, involve alterations in spatial self-representation. The sense of being located in a body or having defined bodily boundaries changes or dissolves. Neuroscience attributes these experiences to altered activity in temporoparietal junction and posterior parietal cortex, regions integrating multisensory signals to construct body representation. If meditation alters these regions' activity, unusual bodily experiences might result. Whether such experiences have lasting impact on self-concept or well-being is unknown. Mystical experiences characterized by ineffability, noetic quality, transcendence of time and space, sense of unity, and positive affect occur across contemplative traditions. Psychedelics reliably produce mystical experiences, and meditation can as well, though less predictably and typically requiring extensive practice. The neural correlates of mystical experiences include decreased DMN activity, altered connectivity between networks, and patterns overlapping with psychedelic-induced states. Whether mystical experiences have intrinsic value or therapeutic benefit independently of the meaning individuals attribute to them is debated. The relationship between meditation-induced and psychedelic-induced mystical experiences raises interesting questions. Do they involve identical neural mechanisms and subjective qualities, or are there important differences? Can psychedelics shortcut the gradual meditation path to mystical states, or do they produce superficially similar but fundamentally different experiences? Some research suggests mystical experiences, regardless of induction method, produce lasting positive changes, including increased well-being, prosociality, and even liberal political attitudes. Investigating mechanisms could clarify what features are essential for transformation. Longitudinal phenomenological studies tracking practitioners over years of intensive practice could document experiential changes and identify markers of developmental stages. Combining detailed first-person reports with periodic neuroimaging, behavioral testing, and biological sampling would provide unprecedented data on how human consciousness and brain transform with sustained contemplative training. Such studies are resource-intensive, but could revolutionize understanding of neuroplasticity, consciousness, and human development. The question of enlightenment or awakening, whether meditation can produce permanent, irreversible transformations in consciousness, as traditional systems claim, represents perhaps the deepest question for contemplative neuroscience. Practitioners claim that awakening involves permanent recognition of the nature of mind, elimination of certain forms of suffering, and transformation of perception and response to experience. If such transformations exist, what neural changes underlie them? Can neuroscience distinguish awakened from unawakened individuals? Preliminary studies comparing long-term practitioners claiming awakening to matched controls find differences in brain structure, function, and connectivity. But interpreting causality and significance is difficult. Do observed differences cause, result from, or merely correlate with subjective transformation? Are claimed transformations stable across contexts and over time? Do different traditions, awakenings, involve identical or different neural signatures? These questions require longitudinal studies following practitioners before, during, and long after purported awakening experiences. The challenge of validating awakening claims highlights tension between first-person and third-person methods. Awakening is inherently subjective, defined by subjective qualities of experience. Yet neuroscience requires objective measures. Can objective measures ever fully validate subjective transformation? Or must we rely on behavioral and psychological proxies, reduced suffering, enhanced compassion, stable well-being as indicators? The epistemological questions here are profound and may ultimately be irresolvable. If you're still awake somewhere in this exploration of meditation science, of brain changes and attention training, of stress reduction and compassion cultivation, of neuroplasticity and consciousness investigation, of advanced states and molecular mechanisms, of breathing rhythms and contemplative traditions, of research frontiers and ancient wisdom, there's more to discover about these practices transforming minds and bodies across cultures and centuries. But if sleep has found you, if consciousness has faded into dreams, then rest knowing that the very capacity for awareness you've been reading about continues operating, sustaining your existence even as conscious thought dissolves. While you sleep tonight, your brain continues its essential housekeeping, consolidating memories from today, clearing metabolic waste through the glymphatic system, and cycling through sleep stages, each serving specific restorative functions. The default mode network that meditation modulates remains active during certain sleep stages, particularly REM sleep when vivid dreams occur. Your brain generates spontaneous thoughts and images without the regulation meditation cultivates, allowing unconstrained neural activity that may serve creative and emotional processing functions. The stress response systems that meditation helps regulate, your HPA axis and sympathetic nervous system, idle at low levels during deep sleep. Cortisol reaches its daily nadir in early night before beginning to rise toward morning. Growth hormone peaks during slow-wave sleep, supporting tissue repair and growth. These circadian rhythms in hormones represent ancient biological timing systems that meditation practices can help normalize but not fundamentally alter. The body's needs for rest and activity remain. Your cardiovascular system that meditation benefits through reduced blood pressure and improved heart rate variability continues its tireless work. Heart rate and blood pressure decline during sleep, allowing cardiovascular recovery. The parasympathetic dominance of deep sleep provides the opposite of the sympathetic fight-or-flight response, demonstrating the body's capacity for profound relaxation even without meditation training. Sleep itself may represent the ultimate natural meditation on physiological terms. The immune system that meditation supports through reduced inflammation and enhanced function mounts its most vigorous responses during sleep. Sleep deprivation impairs immunity, increasing infection susceptibility. Immune cells release cytokines affecting sleep, creating feedback between sleep and immunity. If meditation improves sleep, some immune benefits might be sleep-mediated rather than direct meditation effects. Untangling these relationships requires careful research designs. Your breathing, the anchor object for many meditation practices, continues rhythmically through sleep, regulated by brainstem respiratory centers without conscious control. Breathing rate and pattern change across sleep stages, more variable during REM, more regular during deep sleep. The coupling between breathing and neural rhythms persists during sleep, with slow cortical oscillations synchronizing to respiration. This breath-brain coupling that meditation harnesses for voluntary attention training operates automatically throughout sleep. The hippocampus that shows structural increases with meditation practice actively consolidates memories during sleep, replaying patterns of neural activity from waking experience. This consolidation strengthens memories and integrates new learning with existing knowledge. If meditation enhances neuroplasticity, it might synergize with sleep-dependent consolidation, though this possibility requires investigation. The relationship between meditation, sleep, and memory formation represents an understudied but potentially important intersection. Your prefrontal cortex that meditation strengthens is relatively deactivated during sleep, particularly during REM sleep, when executive control diminishes, allowing bizarre dream scenarios to unfold without reality testing. The reduced prefrontal activity in dreams resembles psychosis or psychedelic states in some respects, generating experiences unconstrained by normal cognitive control. This nightly prefrontal deactivation contrasts with meditation's prefrontal engagement, highlighting different brain states serving different functions. The amygdala that meditation helps regulate shows differential activity across sleep stages. During REM sleep, the amygdala activates while the prefrontal cortex deactivates, allowing emotional processing without top-down inhibition. This combination may facilitate emotional memory consolidation and regulation through distinct mechanisms from wake meditation. Sleep and meditation might offer complementary pathways to emotional well-being: meditation through conscious regulation, sleep through unconscious processing. Consider that meditation and sleep represent different alterations of consciousness with different functions. Meditation involves intentional transformation of waking awareness through systematic mental training. Sleep involves cycling through distinct stages, serving physiological and cognitive restoration. Both involve reduced external attention and sensory processing, but meditation maintains meta-awareness, while sleep largely abolishes it. Understanding how these states relate and potentially synergize could illuminate consciousness and well-being. The research on meditation remains young relative to the millennia-long history of contemplative practices. Modern neuroscience has only begun to investigate what dedicated practitioners have explored for centuries: the malleability of attention, emotion, and consciousness through systematic training. The convergence of ancient wisdom and modern science has potential to benefit both. Science gains access to sophisticated phenomenological methodologies and deep practitioners, while contemplative traditions gain empirical validation and mechanistic understanding. The challenges facing meditation science are substantial. Meditation involves subtle subjective experiences difficult to operationalize and measure. Individual differences in practice quality, motivation, and capacity create noise in data. Expectation effects and placebo responses complicate interpretation. Long-term effects require years of study. Traditional practices embedded in cultural contexts may not translate directly to secular applications. These challenges require methodological innovation and humility about limitations. Yet the promise of meditation science is equally substantial. Understanding how intentional mental training restructures brain and body could revolutionize approaches to mental health, education, human development, and our understanding of consciousness itself. If meditation represents a technology for transforming subjective experience and optimizing brain function, reverse engineering its mechanisms could yield insights applicable far beyond meditation, per se, to mental training in general, to consciousness science, to human flourishing. The democratization of meditation through apps, online courses, and secular programs has made practices once restricted to monastics or special initiates accessible to millions. This accessibility has benefits: reducing suffering through stress reduction and mental health applications, but also risks: oversimplification of complex practices, commodification of ancient wisdom, and separation from ethical frameworks giving practices deeper meaning. Balancing accessibility and integrity remains an ongoing challenge. Meditation cannot solve all problems or substitute for systemic changes addressing injustice, inequality, and environmental destruction. Meditation helps individuals work skillfully with their own minds, but doesn't address external conditions requiring collective action. Overstating meditation's benefits or presenting it as a panacea risks perpetuating spiritual bypassing, using meditation to avoid rather than address genuine problems. Meditation is most powerful when combined with wise action in the world. The subjective experience of meditation, what it's like from the inside, remains the heart of practice even as neuroscience reveals correlates and mechanisms. Brain scans can show which regions activate during meditation, but cannot capture the quality of concentrated awareness, the dissolution of self-boundaries, the arising of compassion, or the direct perception of impermanence. Science and phenomenology offer complementary perspectives, both necessary for complete understanding. Different meditation traditions emphasize different aspects and aims. Theravada Buddhism emphasizes mindfulness and insight into the nature of experience. Tibetan Buddhism emphasizes compassion and elaborate visualization practices. Zen emphasizes sudden realization of Buddha nature through koan contemplation or shikantaza. Hindu yoga emphasizes union with the divine through various paths. Taoist meditation emphasizes naturalness and harmony with the Tao. Modern secular approaches emphasize stress reduction and well-being. Each tradition offers unique perspectives and techniques deserving investigation. The universality of contemplative practices across cultures suggests they address fundamental aspects of human psychology and potential. Virtually every culture has developed practices involving sustained attention, introspection, and consciousness exploration. This universality might reflect common neural architecture permitting these capacities, common human existential concerns motivating their cultivation, or both. Cross-cultural investigation of meditation could reveal universal versus culture-specific aspects. Meditation's future likely involves continued integration with psychotherapy, medicine, education, and workplace wellness programs. Scientific understanding will deepen through neuroimaging advances, larger studies, better controls, and mechanistic investigation. Technology including neurofeedback, brain stimulation, and virtual reality might augment traditional practices. Global spread will continue as practices adapt to diverse cultures. Understanding will progress through ongoing dialogue between science and contemplative traditions. The ultimate questions about meditation transcend neuroscience, questions about meaning, purpose, and the good life. Does meditation cultivate human flourishing in Aristotelian terms? Does it alleviate suffering in Buddhist terms? Does it reveal fundamental truths about mind and reality? Can scientific investigation address such questions, or do they require philosophical and experiential investigation? These questions ensure that meditation research remains not just technical, but profoundly human. Your own experience with meditation, should you choose to explore it, would provide the most direct knowledge. Reading about brain changes and physiological effects reveals what meditation does, but practicing reveals what meditation is. The subjective transformation of sitting quietly, observing breath, noticing thoughts arise and pass, recognizing the space of awareness in which experience unfolds. This cannot be conveyed fully through description. It must be experienced directly. See you next time.